The universe, as we understand it, begins not with a boundary in space, but with a boundary in perception. When we look up at the night sky, what we see feels endless, scattered with stars that seem to stretch forever in every direction. Yet this sense of infinity is deceptive. There is a limit to what we can observe, not because the universe necessarily ends, but because light itself has a finite speed, and time has a beginning. Everything we see is shaped by this simple but profound constraint. The observable universe is not the whole universe. It is only the portion from which light has had enough time to reach us since the beginning of cosmic expansion. To grasp this idea, imagine standing in a vast, dark ocean with a small lantern. The light from the lantern spreads outward, illuminating only a limited area around you. Beyond that circle of light, there may be more water, more waves, even entire islands, but they remain hidden in darkness because the light has not reached them. In a similar way, our view of the universe is defined by how far light has traveled over billions of years. This distance creates a kind of cosmic horizon, a sphere centered on us, beyond which we cannot see. This horizon is not a physical wall or an edge in the traditional sense. It is not something you could travel to and touch. Instead, it is a limit set by time and the speed of light. The universe is approximately 13.8 billion years old, and light travels at a constant speed. At first glance, it might seem that the observable universe should extend 13.8 billion light-years in every direction. However, the reality is far more complex because space itself has been expanding during that time. As light travels through the cosmos, the distances between galaxies grow, stretching the journey and pushing the observable boundary even farther out. As a result, the radius of the observable universe is estimated to be about 46 billion light-years. This means that the full observable diameter is roughly 93 billion light-years across. This number can be difficult to comprehend. It represents not just distance, but time, motion, and the dynamic nature of space itself. When we observe distant galaxies, we are not seeing them as they are today. We are seeing them as they were billions of years ago, when the light we now detect first began its journey toward us. This concept transforms the night sky into a kind of time machine. Every point of light is a glimpse into the past. Nearby stars appear as they were a few years ago. Distant galaxies appear as they were millions or even billions of years ago. The farther we look, the deeper into the past we see. At the extreme edge of the observable universe, we encounter the oldest light of all, a faint glow known as the cosmic microwave background. This radiation is a remnant of the early universe, released when the cosmos cooled enough for light to travel freely for the first time. Before that moment, the universe was opaque, filled with a hot, dense plasma that scattered light in all directions. Photons could not travel freely, so there was no clear image of the universe. When the plasma cooled and atoms formed, light was finally able to move unhindered, creating a snapshot of the universe at that early stage. This ancient light still fills the cosmos today, stretched and cooled by expansion, providing a glimpse of the universe when it was only a few 100,000 years old. The observable universe is therefore not just a region of space, but a record of cosmic history. It contains layers of time, each corresponding to a different distance and era. As we look outward, we are also looking backward, peeling away the history of the cosmos layer by layer. This dual nature of distance and time is one of the most fascinating aspects of astronomy, revealing a universe that is both vast and deeply interconnected. Yet, the existence of an observable limit raises an important question. If there is a boundary to what we can see, what lies beyond it? The answer is both simple and mysterious. Beyond the observable universe, there may be more of the same, more galaxies, more stars, more cosmic structures extending far beyond our reach. The laws of physics that govern our region of the universe are likely the same elsewhere, suggesting a continuity that stretches into the unknown. However, because light from those regions has not had time to reach us, they remain forever hidden from direct observation. This limitation is not due to technological constraints. Even the most powerful telescopes cannot see beyond the observable universe because the information simply has not arrived. No matter how advanced our instruments become, we are bound by the fundamental laws of physics. The speed of light acts as a cosmic speed limit, ensuring that some regions will always remain inaccessible. Another layer of complexity arises from the expansion of space itself. As the universe expands, distant galaxies move away from us. For very distant objects, this motion can exceed the speed of light, not because they are moving through space that quickly, but because space itself is stretching between us. This means that light emitted by some galaxies today will never reach us, as the space between us and them expands faster than the light can travel. These galaxies effectively slip beyond our observable horizon, becoming permanently invisible. This dynamic nature of the observable universe means that it is not fixed. It evolves over time. As more light reaches us, our observable region grows, revealing new parts of the cosmos. At the same time, the accelerated expansion driven by dark energy causes some regions to recede beyond our reach. The balance between these processes shapes the future of what we can observe, gradually isolating us from distant parts of the universe. The concept of the observable universe also challenges our intuitive understanding of position and perspective. From our point of view, we appear to be at the center of this observable sphere. However, this does not mean that we occupy a special place in the cosmos. Every observer, regardless of their location, would see a similar sphere centered on themselves. This is a consequence of the uniform expansion of space, which ensures that the large-scale structure of the universe looks roughly the same from any vantage point. This idea reinforces a fundamental principle of cosmology, that the universe is homogeneous and isotropic on large scales. In simpler terms, it means that the universe is broadly the same everywhere and in all directions. While local variations exist, such as galaxies, clusters, and voids, the overall structure follows consistent patterns. This uniformity allows scientists to make meaningful observations and develop models that describe the universe as a whole. Despite this uniformity, the observable universe is filled with extraordinary diversity. It contains hundreds of billions of galaxies, each with billions of stars, planets, and potentially life. These structures form intricate patterns, from vast filaments stretching across space to enormous voids where few galaxies exist. Together, they create a cosmic web, a large-scale structure that reveals the influence of gravity over billions of years. The study of the observable universe relies on a combination of observation and theory. Telescopes capture light across different wavelengths, from visible light to radio waves and X-rays, allowing scientists to probe different aspects of the cosmos. Meanwhile, theoretical models help interpret these observations, providing insights into the underlying processes that shape the universe. Together, they form a powerful framework for understanding the cosmos, even within the limits imposed by observation. As we continue to explore the observable universe, we refine our understanding of its size, age, and composition. We have discovered that ordinary matter, the stuff that makes up stars, planets, and living beings, accounts for only a small fraction of the total. The rest consists of dark matter and dark energy, mysterious components that influence the structure and expansion of the universe. These discoveries remind us that even within the observable realm, much remains unknown. The observable universe is both a window and a barrier. It allows us to see vast distances and ancient times, revealing a cosmos of incredible scale and complexity. At the same time, it marks the limits of our knowledge, beyond which lies uncertainty and speculation. This dual nature makes it one of the most intriguing concepts in modern science, inviting both exploration and humility. As we stand on this cosmic threshold, we are reminded that our understanding is shaped by the tools and limits of observation. The universe may extend far beyond what we can see, possibly infinitely, containing regions that will never interact with us in any way. These unseen realms challenge our imagination, pushing us to consider possibilities that lie beyond direct evidence. In the end, the observable universe is not just a scientific concept, it is a profound statement about our place in the cosmos. It tells us that we are part of a vast and dynamic system, connected to distant galaxies through the light that reaches us, yet separated from much of the universe by the fundamental limits of time and space. It is a reminder that knowledge has boundaries, but curiosity does not, and that the quest to understand the universe is as much about exploring those boundaries as it is about expanding them. To understand the scale of the universe, it is necessary to move beyond the familiar measurements of everyday life. On Earth, distance is measured in meters and kilometers, units that are practical for navigating cities and landscapes. Even when we think about traveling across countries or continents, these units remain manageable. However, once we begin to look beyond our planet, these measurements quickly become inadequate. The distances between celestial objects are so vast that they demand a completely different way of thinking, one that stretches the limits of human imagination. The most fundamental unit used to measure cosmic distances is the light year. A light year is not a measure of time, but of distance. It represents how far light can travel in 1 year, moving at a constant speed of about 300,000 kilometers per second. In a single second, light can circle the Earth more than 7 times. Over the course of a year, it travels nearly 9.5 trillion kilometers. This immense distance becomes the baseline for understanding the cosmos, allowing astronomers to express the separation between stars and galaxies in a more meaningful way. Even within our own cosmic neighborhood, distances are staggering. The nearest star system to Earth, Proxima Centauri, is more than 4 light-years away. This means that the light we see from it today began its journey over 4 years ago. If we were to travel to that star using current technology, it would take tens of thousands of years to arrive. This simple fact highlights how isolated we are, even within the relatively small scale of our local stellar environment. As we move beyond nearby stars, the distances grow exponentially. Our galaxy, the Milky Way, spans about 100,000 light-years from one end to the other. It contains hundreds of billions of stars, each separated by vast stretches of space. Traveling across the galaxy at the speed of light would take 100,000 years, and yet this is just one galaxy among countless others scattered throughout the universe. To measure distances beyond our galaxy, astronomers rely on a variety of techniques, each suited to a different scale. One of the earliest methods involves the use of parallax, a phenomenon that occurs when an object appears to shift position against a distant background as the observer moves. By measuring this shift from different points in Earth's orbit, scientists can calculate the distance to nearby stars with remarkable precision. However, this method becomes less effective as distances increase, requiring more advanced techniques for objects farther away. Another important tool is the use of standard candles, objects with known brightness. Certain types of stars, such as Cepheid variables, have a predictable relationship between their brightness and the rate at which they pulsate. By observing how quickly these stars vary in brightness, astronomers can determine their true luminosity. Comparing this intrinsic brightness to how bright they appear from Earth allows scientists to calculate their distance. This method has been crucial in extending our reach beyond the Milky Way and into the realm of other galaxies. For even greater distances, astronomers turn to Type Ia supernovae, powerful stellar explosions that shine with a consistent peak brightness. These events can be observed across vast stretches of space, serving as cosmic beacons that help map the expansion of the universe. By measuring the apparent brightness of these supernovae, scientists can determine how far away they are and how quickly the universe is expanding. One of the most significant discoveries in modern cosmology comes from the observation that distant galaxies are moving away from us. This motion is detected through a phenomenon known as redshift. When light from a galaxy is stretched to longer wavelengths as it travels through expanding space, it shifts toward the red end of the spectrum. The greater the redshift, the faster the galaxy is receding. This relationship, first described by Edwin Hubble, provides a direct link between distance and velocity, allowing astronomers to estimate how far away a galaxy is based on how much its light has been stretched. Redshift not only reveals the motion of galaxies, but also provides evidence for the expansion of the universe itself. It shows that space is not static, but dynamic, constantly stretching and evolving over time. This expansion affects the way we measure distance, making it necessary to consider not just how far light has traveled, but how the fabric of space has changed during that journey. As a result, distance in cosmology is not a simple concept. There are different ways to define it, depending on the context. For example, there is the distance that light has traveled, known as the light travel distance. There is also the current distance to an object, which takes into account the expansion of the universe. These different definitions can lead to seemingly contradictory values, but they all describe different aspects of the same underlying reality. The expansion of the universe also introduces the idea of co-moving distance, a measure that accounts for the stretching of space over time. This allows astronomers to describe the separation between objects in a way that remains consistent even as the universe evolves. By using co-moving coordinates, scientists can map the large-scale structure of the cosmos and understand how galaxies are distributed across vast distances. Mapping the universe is a monumental task that requires both precise measurements and sophisticated models. Large surveys of the sky have revealed a complex web of galaxies, clusters and filaments, forming a structure that resembles a cosmic network. This cosmic web is shaped by gravity, which pulls matter together over billions of years, creating dense regions surrounded by vast empty voids. At the largest scales, the universe appears remarkably uniform. No matter where we look, the distribution of galaxies follows similar patterns, suggesting that the laws of physics are consistent throughout the cosmos. This uniformity supports the idea that the universe began in a hot, dense state and has been expanding and evolving ever since. Despite the progress made in measuring cosmic distances, there are still uncertainties and challenges. Each method has its limitations, and small errors can accumulate over vast scales. To improve accuracy, astronomers use multiple techniques and cross-check their results, building a more reliable picture of the universe. One of the most ambitious goals in cosmology is to determine the exact rate of expansion of the universe, known as the Hubble constant. This value is crucial for understanding the age, size, and fate of the cosmos. However, different methods of measuring the Hubble constant have produced slightly different results, leading to an ongoing debate known as the Hubble tension. This discrepancy suggests that there may be new physics waiting to be discovered, hidden within the complexities of cosmic measurement. The quest to measure the universe is not just about numbers. It is about understanding our place within an immense and ever-changing cosmos. Each distance measurement represents a connection between us and a distant object, a bridge formed by light traveling across unimaginable spans of space and time. Through these measurements, we piece together a map of the universe, revealing its structure and history in ever greater detail. As our tools and techniques continue to improve, we push the boundaries of what can be measured. New telescopes and observatories are designed to probe deeper into space, capturing light from the earliest galaxies and shedding light on the formation of cosmic structures. These observations allow us to refine our models and test our understanding of the universe, bringing us closer to answering some of the most profound questions in science. Yet, even as we expand our reach, we remain bound by the limits of the observable universe. There will always be regions beyond our ability to measure, hidden behind the cosmic horizon. These unseen areas remind us that our map of the universe is incomplete, a fragment of a much larger reality that extends beyond our perception. The act of measuring the cosmos is both a scientific endeavor and a philosophical journey. It forces us to confront the scale of existence and the limits of human understanding. It challenges us to think in ways that go beyond everyday experience, embracing concepts that stretch the imagination and redefine what it means to explore. In the end, the effort to measure the universe is a testament to human curiosity and ingenuity. It shows how far we have come from simply gazing at the stars to unraveling the structure of the cosmos. It also highlights how much remains to be discovered, inviting us to continue exploring, questioning, and seeking answers in the vast expanse of space. The story of the universe begins with a moment that defies ordinary understanding, a moment when space, time, energy, and matter all emerged from an avasta so extreme that the laws of physics as we know them begin to break down. This moment is known as the Big Bang, not an explosion in space, but an expansion of space itself. It marks the beginning of everything we can observe, the origin point from which the entire cosmos has evolved over billions of years. To understand the present universe, we must travel back in time to this earliest epoch and follow the unfolding of cosmic history from its very first moments. In the beginning, the universe was unimaginably hot and dense. There were no stars, no galaxies, no atoms, not even the basic particles that make up matter today. Instead, the universe existed as a seething, energetic state where temperature and density were so high that conventional structures could not form. Space itself was compressed into a state far smaller than anything we can easily imagine, yet it contained all the energy that would eventually give rise to every galaxy, every star, and every planet. As the universe began to expand, it also began to cool. This cooling allowed energy to transform into particles, giving rise to the fundamental building blocks of matter. Quarks and electrons emerged from the energetic chaos, and within fractions of a second, quarks combined to form protons and neutrons. These particles would later become the nuclei of atoms, but in these early moments, the universe was still too hot for stable atomic structures to exist. One of the most important phases in the early universe is known as cosmic inflation, a brief period of extremely rapid expansion that occurred within a tiny fraction of a second after the Big Bang. During this phase, the universe expanded exponentially, growing from a subatomic scale to something much larger in an instant. This sudden expansion smoothed out irregularities and helped create the large-scale uniformity we observe today. It also stretched tiny quantum fluctuations, turning them into the seeds of future cosmic structures. After inflation ended, the universe continued to expand, but at a slower and more steady rate. As it cooled further, protons and neutrons began to combine to form the nuclei of simple elements, primarily hydrogen and helium. This process, known as nucleosynthesis, occurred within the first few minutes of cosmic history. The proportions of these elements provide important evidence for the Big Bang model, as they match the predictions made by theoretical calculations. For hundreds of thousands of years after nucleosynthesis, the universe remained a hot, dense plasma composed of charged particles and photons. Light could not travel freely during this time because it was constantly scattered by electrons. The universe was effectively opaque, with no clear path for light to move through. This changed as the temperature dropped to a point where electrons could combine with atomic nuclei to form neutral atoms. This event, known as recombination, marked a turning point in cosmic history. When atoms formed, photons were finally able to travel freely through space. This release of light created what we now observe as the cosmic microwave background, a faint radiation that fills the universe and serves as a snapshot of the cosmos at that early time. This ancient light provides a wealth of information about the conditions of the early universe, revealing tiny variations in temperature that correspond to the initial density fluctuations. These fluctuations, though incredibly small, played a crucial role in shaping the universe. Regions with slightly higher density exerted a stronger gravitational pull, attracting more matter and gradually growing over time. This process led to the formation of the first structures, including stars and galaxies. Over billions of years, these structures evolved into the vast cosmic web we observe today, with clusters of galaxies connected by filaments and separated by enormous voids. The expansion of the universe is a central feature of this entire process. As space expands, the distances between galaxies increase, and the wavelength of light traveling through space is stretched. This stretching is what produces the redshift observed in distant galaxies, providing direct evidence for the ongoing expansion of the cosmos. The rate of this expansion has changed over time, influenced by the balance between gravity and other forces. In the early universe, gravity played a dominant role, slowing the rate of expansion as matter pulled itself together. However, at later times, a mysterious force known as dark energy began to dominate, causing the expansion to accelerate. This shift has profound implications for the future of the universe, as it suggests that galaxies will continue to move farther apart at an increasing rate. Understanding the Big Bang is not just about looking backward in time. It is also about understanding the fundamental laws that govern the universe. The conditions of the early universe provide a natural laboratory for testing theories of physics at extreme energies and densities. By studying the remnants of these early moments, such as the cosmic microwave background and the distribution of galaxies, scientists can gain insights into the nature of space, time, and matter. Despite the success of the Big Bang model, there are still unanswered questions. One of the most significant is what happened at the very beginning, at the exact moment of the Big Bang. Current theories break down under such extreme conditions, and a complete understanding likely requires a theory of quantum gravity, which would unify general relativity with quantum mechanics. This remains one of the greatest challenges in modern physics. Another mystery is the nature of dark matter and dark energy, which together make up the majority of the universe's content. Dark matter provides the gravitational framework that allows galaxies to form and remain stable, while dark energy drives the accelerated expansion of the universe. Although their effects are well documented, their true nature remains unknown, adding another layer of complexity to our understanding of cosmic evolution. The timeline of the universe is a story of transformation, from simplicity to complexity. It begins with a nearly uniform state, and evolves into a richly structured cosmos filled with galaxies, stars, and planets. This evolution is driven by the interplay of fundamental forces, the expansion of space, and the influence of unseen components like dark matter and dark energy. As we observe distant objects, we are effectively looking back in time, tracing this evolution step by step. The most distant galaxies we can see provide a glimpse of the universe when it was only a fraction of its current age. These observations help fill in the gaps between the early universe and the present day, creating a continuous narrative that spans billions of years. The Big Bang model also implies that the universe has a finite age, a beginning in time. This idea has profound philosophical implications, challenging older notions of an eternal and unchanging cosmos. It raises questions about what, if anything, came before the Big Bang, and whether the concept of "and quote" before "and quote" even has meaning in this context. These questions push the boundaries of science and enter the realm of philosophy, where definitive answers may be difficult to obtain. At the same time, the success of the Big Bang theory demonstrates the power of scientific inquiry. By combining observation, theory, and experimentation, scientists have been able to reconstruct the history of the universe with remarkable precision. This achievement reflects centuries of progress, from early observations of the night sky to modern measurements using advanced technology. The expansion of the universe continues to shape its future. As galaxies move farther apart, the night sky will gradually change. In the distant future, observers in our galaxy may see fewer and fewer galaxies, as many drift beyond the observable horizon. This isolation will alter the way future civilizations understand the universe, potentially limiting their ability to reconstruct its history. For now, we exist at a time when the universe is both observable and comprehensible to a significant degree. We can see distant galaxies, detect ancient radiation, and measure the expansion of space. This unique vantage point allows us to explore the origins and evolution of the cosmos, piecing together a story that spans nearly 14 billion years. The Big Bang is not just a theory about the past, it is a framework that connects the past, present, and future of the universe. It explains how the cosmos came to be, how it has changed over time, and how it may continue to evolve. It provides a foundation for understanding everything from the smallest particles to the largest structures, linking them together in a coherent and comprehensive picture. As we continue to study the universe, new discoveries will refine and expand this picture. Observations of distant galaxies, measurements of cosmic radiation, and advances in theoretical physics will all contribute to a deeper understanding of the Big Bang and its consequences. Each new piece of information brings us closer to answering fundamental questions about the nature of reality. In the end, the story of the Big Bang is a story of beginnings. It is the starting point of the observable universe, the moment from which all cosmic history unfolds. It reminds us that the universe is not static, but dynamic, constantly evolving and changing over time. It invites us to explore, to question, and to seek a deeper understanding of the cosmos and our place within it. As we push our understanding of the universe further, we encounter a concept that challenges even the most imaginative interpretations of space and time. This concept is known as the cosmic horizon, a boundary that defines not just what we can see, but what we can ever hope to observe, no matter how advanced our technology becomes. Unlike physical borders on Earth, this boundary is not fixed in place or made of any substance. It is shaped by the laws of physics, the expansion of the universe, and the passage of time itself. To understand the cosmic horizon, it is useful to think about the relationship between distance and time in the universe. Light travels at a constant speed, and because the universe has a finite age, there is a maximum distance from which light has had enough time to reach us. This creates what is known as the particle horizon, the outermost boundary of the observable universe. Everything within this horizon is, in principle, visible to us, because its light has had sufficient time to arrive since the beginning of cosmic expansion. However, the story does not end there. The universe is not static. It is expanding, and that expansion is accelerating due to the influence of dark energy. This introduces another type of boundary known as the event horizon. While the particle horizon marks the limit of what we can currently see, the event horizon defines the limit of what we will ever be able to see in the future. Light emitted today from beyond this horizon will never reach us, no matter how long we wait, because the space between us and those regions is expanding too quickly. This distinction between the particle horizon and the event horizon is crucial for understanding the limits of observation. The particle horizon is like a record of the past, showing us how far light has traveled since the beginning of the universe. The event horizon, on the other hand, is a prediction about the future, indicating which regions of space will remain forever inaccessible. Together, they define the boundaries of our observable reality. The existence of these horizons is a direct consequence of the expansion of space. As the universe expands, the distances between galaxies increase. For nearby galaxies, this expansion is relatively small, and their light can still reach us. But for galaxies that are sufficiently distant, the expansion becomes dominant, stretching the space between us faster than light can traverse it. In such cases, even though light is always moving at its maximum speed, it can never overcome the expansion, effectively trapping it beyond our reach. This leads to a surprising and somewhat counterintuitive conclusion. There are regions of the universe that are receding from us faster than the speed of light, yet this does not violate the laws of physics. The speed limit imposed by relativity applies to objects moving through space, not to the expansion of space itself. As space expands, it can carry galaxies with it, increasing the distance between them at a rate that exceeds the speed of light, without breaking any fundamental rules. The cosmic horizon is therefore not a static boundary, but a dynamic one. As time passes, the particle horizon grows, allowing us to see more of the universe. Light that was once too distant to reach us eventually arrives, revealing new regions of space. At the same time, the event horizon can shrink in a relative sense, as more galaxies cross it and become permanently unobservable. This creates a complex interplay between visibility and invisibility, shaping our view of the cosmos over time. The concept of horizons also has profound implications for our understanding of causality. In everyday life, we assume that events can influence one another as long as there is enough time for signals to travel between them. In the universe, this principle still applies, but it is limited by the cosmic horizon. Regions beyond our event horizon are causally disconnected from us, meaning that no signal or influence from those regions can ever reach us. They exist, in a sense, beyond our causal universe, separate and inaccessible. This idea challenges our intuitive sense of reality. It suggests that the universe is larger than the portion we can interact with, containing vast regions that are forever beyond our reach. These regions may be governed by the same physical laws, or they may differ in ways we cannot detect. The cosmic horizon ensures that, regardless of their nature, they remain hidden from direct observation. Another fascinating aspect of cosmic horizons is how they affect the future of observation. As the universe continues to expand at an accelerating rate, more and more galaxies will cross the event horizon. Over billions of years, distant galaxies will fade from view, their light stretched to longer wavelengths and eventually disappearing altogether. In the far future, observers in our galaxy may see only a small fraction of the universe we observe today, with most galaxies having receded beyond visibility. This gradual isolation has significant consequences for the study of cosmology. Future civilizations may not have access to the same wealth of observational data that we currently possess. Without visible evidence of distant galaxies or the cosmic microwave background, it may be much harder to reconstruct the history of the universe or understand its large-scale structure. In this sense, we live in a fortunate era when the universe is still accessible enough to reveal its secrets. The cosmic horizon also plays a role in shaping the distribution of information in the universe. Because signals cannot travel faster than light, and because the expansion of space limits how far those signals can go, information is confined within certain regions. This creates a patchwork of observable domains, each with its own accessible history and structure. While these domains may overlap to some extent, there are always limits beyond which information cannot pass. In theoretical physics, the concept of horizons extends beyond cosmology. Similar ideas appear in the study of black holes, where an event horizon marks the boundary beyond which nothing can escape. Although the mechanisms are different, the underlying principle is the same. Horizons define limits, separating regions of space that can communicate with one another from those that cannot. This connection highlights the deep interplay between gravity, space, and time across different scales. The existence of cosmic horizons also raises philosophical questions about the nature of knowledge and observation. If there are regions of the universe that we can never observe, how can we make statements about them? Scientists approach this challenge by relying on the assumption that the laws of physics are consistent throughout the universe. This principle, known as the cosmological principle, allows us to extrapolate our understanding beyond the observable region. While this approach is supported by evidence within our horizon, it remains an assumption when applied to regions beyond it. Despite these limitations, the study of cosmic horizons provides valuable insights into the structure and evolution of the universe. By understanding how these boundaries form and change over time, scientists can refine their models and make predictions about the future of the cosmos. Observations of distant galaxies, measurements of cosmic expansion, and studies of the cosmic microwave background all contribute to this understanding, revealing the influence of horizons on the observable universe. One of the most intriguing implications of cosmic horizons is the possibility that the universe is far larger than we can ever observe. If the observable universe is just a small part of a much larger whole, then the majority of the cosmos lies beyond our reach. This idea expands the scale of the universe to levels that are almost impossible to comprehend, suggesting that what we see is only a tiny fraction of what exists. At the same time, the observable universe contains more than enough complexity and diversity to challenge our understanding. Within our cosmic horizon, there are billions of galaxies, each with its own unique properties and history. Studying these galaxies provides a window into the processes that shape the universe, from the formation of stars to the evolution of large-scale structures. Even within these limits, the scope of exploration is vast. The cosmic horizon serves as both a boundary and an invitation. It marks the edge of what we can know through direct observation, but it also encourages us to explore the limits of theory and imagination. By pushing against this boundary, scientists seek to uncover deeper truths about the universe, developing new models and ideas that extend beyond the observable realm. As we continue to study the cosmos, our understanding of horizons may evolve. New discoveries could reveal subtle effects or provide indirect evidence about regions beyond our current limits. Advances in technology and theory may allow us to probe deeper into the early universe, approaching the particle horizon with greater precision. While we may never directly observe beyond the cosmic horizon, we can continue to expand our knowledge up to its very edge. In the end, the concept of the cosmic horizon reminds us that the universe is not just vast, but structured in a way that defines what can and cannot be known. It highlights the interplay between light, time, and expansion, showing how these factors combine to shape our view of reality. It also underscores the idea that knowledge has limits, boundaries set not by our lack of effort, but by the fundamental nature of the universe itself. Standing at this boundary, we are faced with a profound realization. There are parts of the universe that we will never see, never measure, and never fully understand through observation alone. Yet, this limitation does not diminish the value of what we can know. Instead, it adds depth and mystery to the cosmos, reminding us that exploration is not just about reaching new places, but about understanding the limits of our reach and the vastness that lies beyond. As scientists explored the expansion of the universe in greater detail, they expected to find that gravity would gradually slow it down. After all, every galaxy, star, and particle exerts a gravitational pull on every other, and over time, this collective attraction should act like a cosmic brake, reducing the rate of expansion. For decades, this assumption shaped our understanding of the universe's future. Some believed the expansion might eventually stop and reverse, leading to a collapse known as the Big Crunch. Others thought it might slow just enough to approach a stable state, but as observations became more precise, a very different and far more surprising picture emerged. In the late 20th century, astronomers studying distant Type Ia supernovae made a discovery that would transform cosmology. These stellar explosions, used as reliable distance markers, revealed that galaxies were not just moving away from each other, but doing so at an increasing rate. The expansion of the universe was accelerating. This finding was unexpected and difficult to explain using known forms of matter and energy. Something unseen was pushing the universe apart, overcoming the pull of gravity on the largest scales. This mysterious force came to be known as dark energy. Unlike ordinary matter, which clumps together under gravity, dark energy appears to be evenly distributed throughout space. It does not form stars or galaxies, and it does not interact with light in any detectable way. Its presence is inferred solely from its effect on the expansion of the universe. Despite being invisible and poorly understood, dark energy is believed to make up about 70% of the total energy content of the cosmos, making it the dominant component of the universe. One way to think about dark energy is as a property of space itself. As space expands, more of it comes into existence, and with it, more dark energy. This leads to a self-reinforcing effect. The more the universe expands, the more dark energy there is to drive further expansion. This feedback loop results in the acceleration observed in distant galaxies, pushing them away from each other at ever-increasing speeds. The idea that empty space could have energy is not entirely new. In quantum physics, even a perfect vacuum is not truly empty. It is filled with fleeting fluctuations, tiny bursts of energy that appear and disappear on extremely short timescales. Some theories suggest that dark energy may be related to this vacuum energy, although the exact connection remains one of the biggest unsolved problems in physics. The predicted value of vacuum energy from quantum theory is vastly larger than what is observed, leading to a profound mismatch that scientists are still trying to resolve. Another way to describe dark energy is through the cosmological constant, a term originally introduced by Albert Einstein. He added this constant to his equations of general relativity to allow for a static universe, which was the prevailing belief at the time. When the expansion of the universe was later discovered, Einstein reportedly abandoned the idea, calling it his greatest mistake. However, the concept of the cosmological constant has since been revived as a possible explanation for dark energy, representing a constant energy density that fills space uniformly. Despite these theoretical frameworks, the true nature of dark energy remains elusive. It could be a constant property of space, or it could be something more dynamic, changing over time. Some theories propose the existence of a new field or form of energy that evolves as the universe expands. Others suggest that our understanding of gravity itself may need to be revised on cosmic scales. Each possibility carries profound implications for the fate of the universe and the laws that govern it. The effects of dark energy become more pronounced over vast distances and long periods of time. In the early universe, matter was much more densely packed, and gravity dominated the dynamics of expansion. Galaxies formed, clusters emerged, and large-scale structures took shape under the influence of gravitational attraction. As the universe expanded and matter became more spread out, the influence of dark energy grew stronger. Eventually, it overtook gravity as the dominant force, leading to the accelerated expansion we observe today. This shift has a direct impact on the observable universe. As expansion accelerates, distant galaxies move away from us more rapidly. Light from these galaxies becomes increasingly redshifted, stretched to longer wavelengths as it travels through expanding space. For galaxies beyond a certain distance, the expansion is so strong that their light can never reach us. They effectively disappear from the observable universe, crossing the cosmic event horizon and becoming permanently inaccessible. Over time, this process will continue, gradually isolating galaxies from one another. In the far future, observers in any given galaxy will see fewer and fewer neighboring galaxies, as most drift beyond visibility. Eventually, only the gravitationally bound structures, such as galaxy clusters, will remain intact. Everything else will recede into darkness, leaving behind a universe that appears much smaller and emptier than it does today. The long-term consequences of dark energy lead to a scenario often referred to as the Big Freeze, or heat death of the universe. In this scenario, the expansion continues indefinitely, causing galaxies to move farther apart and star formation to gradually cease. Existing stars will burn out over trillions of years, leaving behind remnants such as white dwarfs, neutron stars, and black holes. With no new stars forming and energy becoming increasingly dispersed, the universe will approach a state of maximum entropy, where all processes slow to a near halt. However, the story does not necessarily end there. Some models of dark energy suggest that its strength could increase over time. In an extreme case, this could lead to a scenario known as the Big Rip, where the expansion becomes so intense that it eventually tears apart galaxies, stars, planets, and even atomic structures. While current observations do not strongly support this outcome, it remains a possibility that depends on the precise nature of dark energy. Understanding dark energy is one of the central challenges of modern cosmology. It requires not only precise observations, but also new theoretical insights that may reshape our understanding of the universe. Large surveys of galaxies, measurements of cosmic background radiation, and studies of gravitational lensing all contribute to this effort, providing clues about how dark energy behaves and how it influences cosmic evolution. The discovery of dark energy also highlights the importance of questioning assumptions. For many years, the idea of a slowing universe seemed reasonable and consistent with known physics. It took careful observation and analysis to reveal that reality was more complex and surprising. This serves as a reminder that the universe often defies expectations, requiring us to remain open to new ideas and willing to revise our understanding. Dark energy also deepens the mystery of the cosmos by revealing how much we do not yet know. Despite its dominance, it remains invisible and poorly understood, a hidden force shaping the destiny of the universe. Its existence suggests that the universe is governed by components and principles that extend beyond our current knowledge, inviting further exploration and discovery. As we continue to study the expansion of the universe, we refine our measurements and improve our models. New telescopes and instruments allow us to observe distant galaxies with greater precision, track the rate of expansion more accurately, and test different theories of dark energy. Each new observation adds a piece to the puzzle, bringing us closer to understanding this enigmatic force. At the same time, dark energy connects to deeper questions about the nature of reality. It challenges our understanding of space, time, and energy, pushing the boundaries of physics and cosmology. It raises questions about why the universe behaves the way it does and whether there are underlying principles that we have yet to uncover. In the context of the observable universe, dark energy plays a crucial role in defining its limits. By driving accelerated expansion, it shapes the cosmic horizon, determining which regions remain visible and which slip beyond our reach. It influences not only the structure of the universe, but also our ability to observe and understand it. The presence of dark energy transforms the universe from a place governed solely by gravity to one shaped by a delicate balance of forces. This balance determines the past, present, and future of cosmic evolution, influencing everything from the formation of galaxies to the ultimate fate of the cosmos. As we look out into the depths of space, we are witnessing the effects of dark energy in real time. Galaxies drift apart, light stretches across expanding space, and the observable universe evolves with each passing moment. These changes are subtle on human timescales, but over billions of years they reshape the cosmos in profound ways. In the end, dark energy stands as one of the greatest mysteries in science. It is a force that dominates the universe, yet remains largely unknown, a driver of cosmic expansion that challenges our understanding of fundamental physics. It reminds us that even as we uncover the structure and history of the universe, there are still deeper layers waiting to be explored. The study of dark energy is not just about understanding the expansion of the universe. It is about uncovering the fundamental nature of reality, exploring the forces that shape existence on the largest scales. It is a journey into the unknown, guided by observation, theory, and the enduring human desire to understand the cosmos in all its complexity. As the universe continues to expand under the influence of dark energy, the fate of galaxies becomes increasingly tied to distance, gravity, and time. Galaxies are not isolated islands drifting aimlessly through space. They are part of a vast and evolving structure shaped by gravitational attraction and cosmic expansion. While some galaxies remain bound together in clusters and groups, others are gradually carried away by the stretching fabric of space. This separation is not sudden or dramatic on human timescales, but over billions of years, it reshapes the visible universe in profound ways. In the present era, galaxies are still relatively close in cosmic terms. Many are grouped together in clusters bound by gravity, forming dense regions of matter within the larger cosmic web. Our own galaxy, the Milky Way, is part of a small collection known as the local group. Within this group, gravity dominates over cosmic expansion, keeping galaxies bound together despite the overall expansion of the universe. This is why nearby galaxies can still move toward each other and even collide rather than drifting apart. One of the most notable future events involving our galaxy is its eventual collision with the Andromeda galaxy. Despite the expansion of the universe, these two galaxies are gravitationally bound and moving toward each other. Over billions of years, they will merge, forming a single, larger galaxy. This process while violent on a cosmic scale, is unlikely to result in many direct collisions between stars due to the vast distances between them. Instead, it will reshape the structure of both galaxies, triggering new waves of star formation and altering their overall appearance. While local interactions continue, the larger picture tells a different story. Beyond gravitationally bound systems, galaxies are steadily moving away from each other. The expansion of the universe stretches the space between distant galaxies, increasing their separation over time. As this expansion accelerates, driven by dark energy, the rate at which galaxies recede also increases. This leads to a gradual thinning of the observable universe as distant galaxies become harder to detect. Light from these receding galaxies undergoes redshift, stretching to longer wavelengths as it travels through expanding space. Initially, this shift moves light from the visible spectrum into the infrared. But as expansion continues, it can stretch into radio wavelengths and beyond. Eventually, the light becomes so faint and stretched that it is effectively undetectable. From our perspective, these galaxies fade away, not because they cease to exist, but because their light can no longer reach us in a meaningful way. Over immense spans of time, this process leads to a form of cosmic isolation. Galaxies that are not gravitationally bound to us will cross the cosmic event horizon, moving beyond the point where their light can ever reach us again. This means that the observable universe will shrink in a relative sense, even as the actual universe continues to expand. Future observers may find themselves in a cosmos where only a handful of nearby galaxies remain visible, with the rest having vanished beyond the horizon. Within gravitationally bound systems, however, a different evolution unfolds. Galaxies within clusters and groups interact through gravitational forces, merging and reshaping over time. These interactions can trigger bursts of star formation as gas clouds collide and collapse under gravity. Over billions of years, repeated mergers can transform spiral galaxies into larger elliptical galaxies characterized by older stars and less active star formation. As time progresses, the supply of cold gas needed for star formation begins to diminish. Stars form by collapsing clouds of gas, but once this gas is used up or heated beyond the point where it can collapse, the formation of new stars slows and eventually stops. This leads to a gradual aging of galaxies, as existing stars continue their life cycles without being replaced by new ones. Bright, young stars fade, leaving behind older, cooler stars that emit less light. The long-term future of galaxies is therefore marked by a transition from vibrant, star-forming systems to quieter, more stable structures dominated by stellar remnants. White dwarfs, neutron stars, and black holes become increasingly common as stars exhaust their nuclear fuel and reach the end of their life cycles. These remnants continue to exist for vast periods, slowly cooling or interacting with their surroundings in subtle ways. Black holes, in particular, play a significant role in the evolution of galaxies. Supermassive black holes reside at the centers of most galaxies, influencing their dynamics and growth. During galaxy mergers, these black holes can merge as well, releasing enormous amounts of energy in the form of gravitational waves. Over time, black holes may become some of the most dominant objects in the universe, persisting long after stars have faded. Despite their longevity, even black holes are not eternal. According to theoretical predictions, black holes can slowly lose mass through a process known as Hawking radiation. This process is extremely slow for large black holes, taking timescales far beyond the current age of the universe to have a noticeable effect. Nevertheless, it suggests that even the most massive objects will eventually evaporate, contributing to the long-term evolution of the cosmos. As galaxies evolve and the universe expands, the overall structure of the cosmos changes. The large-scale cosmic web, with its filaments and clusters, becomes less connected as distances increase. Regions that were once part of a continuous network become isolated, separated by vast expanses of empty space. This fragmentation reduces the interaction between different parts of the universe, leading to a more uniform and less dynamic cosmic landscape. The fate of galaxies is closely tied to the balance between gravity and expansion. In regions where gravity is strong, structures remain bound and continue to evolve through interactions and mergers. In regions where expansion dominates, galaxies drift apart, becoming increasingly isolated. This dual behavior creates a universe that is both locally complex and globally sparse, with pockets of activity surrounded by vast emptiness. From an observational perspective, the disappearance of distant galaxies has important implications. The night sky, which currently contains countless galaxies visible through telescopes, will gradually become emptier. Over trillions of years, most galaxies will no longer be observable, leaving behind only those within our local gravitational neighborhood. This will fundamentally change how the universe appears to any future observers. In such a distant future, the evidence for cosmic expansion itself may become difficult to detect. Without visible distant galaxies to measure redshift, the expansion of the universe could become less apparent. The cosmic microwave background, already faint, will continue to stretch and cool, eventually becoming undetectable as well. This means that future civilizations might not have access to the same observational clues that have allowed us to understand the universe's history. This possibility highlights the unique position we occupy in cosmic time. We live in an era where the universe is still rich with observable structures, allowing us to study its expansion, composition, and evolution. The data we gather today provides a snapshot of the cosmos at a time when it is both mature and accessible, offering insights that may not be available in the distant future. The evolution of galaxies also reflects broader themes in cosmology, including the interplay between creation and decay. Stars are born, shine brightly, and eventually die, contributing to the ongoing cycle of matter and energy. Galaxies grow through mergers and interactions, then gradually settle into more stable forms. On the largest scales, the universe itself evolves from a dense, energetic beginning to a more diffuse and quiet state. This progression raises questions about the ultimate fate of structure in the universe. Will galaxies continue to exist indefinitely as isolated systems, or will they eventually break down into smaller components? Will black holes dominate the distant future, or will they too fade away, leaving behind a universe filled with low-energy radiation? These questions remain areas of active research, with different models offering different predictions. What is clear is that the universe is not static. It is constantly changing, with galaxies evolving over billions and trillions of years. The processes that shape galaxies today will continue to operate, but their effects will be influenced by the changing conditions of the universe. As expansion accelerates and resources become more limited, the pace and nature of these processes will shift, leading to new stages of cosmic evolution. The study of galaxy evolution provides a window into these long-term changes. By observing galaxies at different distances, we can see them at different stages of their development, effectively looking back in time. This allows us to reconstruct the history of galaxies from their formation in the early universe to their present state. It also helps us predict how they might continue to evolve in the future. In the context of the observable universe, the fate of galaxies underscores the transient nature of what we see. The galaxies visible today are part of a dynamic system that is constantly changing. Some will merge, others will drift away, and many will eventually disappear from view. This impermanence adds a sense of urgency to the study of the cosmos, emphasizing the importance of observation and discovery while the opportunity exists. At the same time, the persistence of gravitationally bound systems provides a form of continuity. Even as the universe expands and distant galaxies vanish, local structures remain, evolving on their own timescales. These systems serve as anchors in an ever-expanding cosmos, maintaining connections that endure long after other regions have become inaccessible. In the end, the fate of galaxies is a story of separation and transformation. It reflects the influence of fundamental forces, the passage of time, and the vast scale of the universe. It shows how structures form, evolve, and eventually fade, contributing to the ongoing evolution of the cosmos. As we look out at the galaxies around us, we are witnessing a moment in this long and complex story. The light we see carries information from the past, revealing how galaxies have changed over billions of years. At the same time, it hints at the future, where many of these galaxies will no longer be visible, having drifted beyond our reach. This dual perspective, looking both backward and forward in time, deepens our understanding of the universe and our place within it. Beyond the limits of the observable universe lies one of the most intriguing and elusive questions in all of cosmology. If what we can see is only a finite region defined by the speed of light and the age of the universe, then what exists outside that boundary? This question does not have a direct observational answer, yet it sits at the heart of our attempt to understand the true scale and nature of the cosmos. The observable universe is like a bubble of visibility, a region illuminated by light that has had time to reach us. Beyond that bubble, there may be vastly more space, filled with galaxies and structures that remain forever hidden from our view. The simplest and most widely accepted idea is that the universe extends far beyond what we can observe, possibly even infinitely. In this view, the observable universe is just a small portion of a much larger whole. The same physical laws that operate within our observable region are assumed to apply everywhere, leading to a universe that is homogeneous and isotropic on large scales. This means that beyond our horizon, there may be more galaxies arranged in similar patterns, forming an endless continuation of the cosmic web. If the universe is indeed infinite, it leads to a number of fascinating implications. An infinite universe would contain an infinite number of galaxies, stars, and planets. Given enough space, even rare events would occur countless times. This raises the possibility that somewhere beyond our observable horizon there could be regions that closely resemble our own, perhaps even containing identical configurations of matter. While this idea is speculative, it emerges naturally from the concept of an infinite and uniform universe. However, the universe does not have to be infinite to extend beyond what we can observe. It could be finite but unbounded, meaning it has a limited size but no edges. This is similar to the surface of a sphere, which has a finite area but no boundaries. If you travel in one direction long enough, you would eventually return to your starting point without ever encountering an edge. In 3 dimensions, such a universe would be difficult to visualize, but it remains a valid possibility within the framework of general relativity. The geometry of the universe plays a key role in determining its overall shape and extent. Observations of the cosmic microwave background suggest that the universe is very close to flat on large scales. A flat universe can be infinite, but it can also be finite if it has a more complex topology. Determining the exact geometry and topology of the universe is an ongoing challenge, requiring precise measurements and careful analysis of cosmic data. Another important consideration is the role of cosmic inflation in shaping the universe beyond our observable limits. During the brief period of rapid expansion in the early universe, space may have grown to an enormous size, far exceeding the region we can currently observe. Inflation could have stretched the universe so much that any curvature or irregularities became effectively undetectable within our observable region. This would make the universe appear flat and uniform, even if it has a more complex structure on larger scales. Inflation also suggests that regions beyond our observable universe may have been causally disconnected from us since the very beginning. This means that they could have developed independently, potentially with different properties or conditions. While the laws of physics are expected to be consistent, there is room for variation in initial conditions, which could lead to differences in the distribution of matter, the formation of structures, or other characteristics. Despite these possibilities, the inability to observe beyond the cosmic horizon places strict limits on what we can know. Science relies on evidence, and without direct or indirect observations, it becomes difficult to test hypotheses about regions beyond our reach. This has led to a careful balance between speculation and evidence in cosmology. Theories about the universe beyond the observable region must be grounded in known physics and consistent with observations within our horizon. One way scientists approach this challenge is by studying the largest observable scales and looking for patterns or anomalies that might hint at what lies beyond. For example, variations in the cosmic microwave background could provide clues about conditions in regions that were once in contact with our observable universe before inflation pushed them beyond reach. While these clues are subtle, they offer a way to probe the boundaries of our knowledge. Another approach involves theoretical models that extend our understanding of physics to larger scales. These models explore different possibilities for the structure and extent of the universe, testing their consistency with known data. While they cannot provide direct answers, they help narrow down the range of possibilities and guide future research. The idea of regions beyond the observable universe also connects to deeper questions about the nature of reality. If there are parts of the universe that we can never observe or interact with, what does it mean to say that they exist? In physics, existence is often tied to observability, but cosmology challenges this notion by suggesting that reality may extend beyond what can be measured. This raises philosophical questions about the limits of knowledge and the role of observation in defining what is real. At the same time, the concept of unseen regions is not entirely unfamiliar. Even within our observable universe, there are areas that are difficult to study directly, such as the interiors of black holes or the earliest moments after the Big Bang. In these cases, scientists rely on indirect evidence and theoretical models to build an understanding. A similar approach can be applied to the universe beyond the observable horizon, using what we know to infer what might exist. The possibility of a vast unseen universe also adds a sense of scale that is difficult to fully grasp. The observable universe already contains billions of galaxies, each with billions of stars. If this is only a small fraction of the total, then the full universe could be orders of magnitude larger, containing an unimaginable amount of matter and energy. This perspective expands our sense of the cosmos, highlighting both its vastness and the limitations of our view. One of the most important aspects of this discussion is the role of assumptions. Much of our understanding of the universe beyond the observable region is based on the assumption that the laws of physics are uniform throughout space. This assumption is supported by observations within our horizon, but it cannot be directly tested beyond it. Nevertheless, it provides a foundation for building models and making predictions about the larger universe. There is also the question of whether new physics might come into play at scales beyond our observation. While current theories have been successful in describing the observable universe, they may not be complete. There could be phenomena or structures that exist beyond our horizon that challenge our current understanding, waiting to be discovered through indirect means or future advancements in theory. The boundary of the observable universe is therefore not just a limit, but a frontier. It represents the edge of what we can know through direct observation, but also the starting point for deeper inquiry. By exploring this frontier, scientists push the limits of knowledge, developing new ideas and testing the boundaries of existing theories. In practical terms, the study of the observable universe remains the primary focus of cosmology. It provides a wealth of data that can be analyzed and understood, offering insights into the history and structure of the cosmos. However, the recognition that there is more beyond this region adds context to these studies, reminding us that what we see is only part of a much larger picture. The concept of regions beyond the observable universe also influences how we think about the origin and fate of the cosmos. If the universe extends far beyond our horizon, then the processes we observe locally may be part of a much broader pattern. This can inform our understanding of cosmic evolution, suggesting that the history we reconstruct from our observations is just one chapter in a much larger story. As we continue to explore the universe, new observations may provide additional clues about what lies beyond. Advances in technology, such as more sensitive detectors and more powerful telescopes, may allow us to probe closer to the cosmic horizon and extract more information from the earliest light. While we may never see beyond the horizon directly, we can continue to refine our understanding of the boundary itself and what it implies. In the end, the question of what lies beyond the observable universe remains open. It is a question that blends science, philosophy, and imagination, inviting us to consider possibilities that extend beyond direct evidence. It challenges us to think about the nature of space, time, and existence on the largest scales, pushing the limits of human understanding. What we do know is that the observable universe is not the whole story. It is a window into a much larger reality, a glimpse of a cosmos that extends far beyond our reach. This realization does not diminish the value of what we can observe. Instead, it adds depth and meaning, reminding us that every discovery is part of a broader quest to understand the universe in its entirety. As we stand at the edge of this cosmic horizon, we are confronted with both knowledge and mystery. We have mapped galaxies, measured expansion, and traced the history of the universe back to its earliest moments. Yet beyond that horizon lies an unknown expanse, waiting not to be seen, but to be understood through the power of thought, theory, and the enduring human desire to explore the infinite. As we move beyond the limits of observation and into the realm of theoretical exploration, one idea stands out for its boldness and its ability to stretch the imagination beyond conventional boundaries. This is the concept of the multiverse, the possibility that our universe is not the only one, but just one of many. While the observable universe already challenges our sense of scale, the multiverse expands that scale even further, suggesting that reality itself may be far larger and more complex than we have ever conceived. The idea of multiple universes does not arise from pure speculation alone. It emerges from attempts to understand the fundamental laws of physics and the conditions of the early universe. In particular, certain models of cosmic inflation suggest that the rapid expansion that occurred shortly after the Big Bang may not have happened just once. Instead, inflation could be an ongoing process, occurring in different regions of space at different times. Each of these regions could form its own universe with its own properties and physical conditions. In this picture, our universe is like a bubble within a much larger cosmic foam. Each bubble represents a separate universe, expanding and evolving independently. These universes may be separated by vast distances or by entirely different dimensions of space and time, making direct interaction between them unlikely or even impossible. The space between these bubbles, if it exists in a meaningful sense, may be governed by laws that are very different from those within any individual universe. One of the most intriguing aspects of the multiverse idea is the possibility that different universes could have different physical constants. In our universe, the laws of physics are defined by a set of constants, such as the strength of gravity, the charge of the electron, and the properties of fundamental particles. These constants determine how matter behaves, how stars form, and whether life can exist. In a multiverse scenario, these constants might vary from one universe to another, leading to a wide range of possible realities. Some universes might have stronger gravity, causing matter to collapse quickly into dense structures. Others might have weaker forces, preventing the formation of galaxies altogether. In some universes, the balance of forces might be just right to allow the formation of complex structures, including stars, planets, and potentially life. This variation raises profound questions about why our universe has the properties it does, and whether those properties are unique or simply one possibility among many. The multiverse concept also provides a possible explanation for the apparent fine-tuning of our universe. Many of the constants of nature appear to be set within narrow ranges that allow for the existence of complex structures. If these values were slightly different, stars might not form, or chemistry might not allow for the development of life. One way to explain this is through the anthropic principle, which suggests that we observe these particular conditions because only universes with such conditions can support observers like us. In a multiverse with countless universes, each with different properties, it is not surprising that at least some would have the right conditions for life. We happen to exist in one of those universes, and therefore we observe the constants that make our existence possible. While this idea does not provide a traditional cause and effect explanation, it offers a way to understand why the universe appears to be so finely balanced. There are several different types of multiverse theories, each arising from different areas of physics. One version comes from inflationary cosmology, where different regions of space undergo inflation at different rates, creating separate universes. Another comes from string theory, which suggests that there may be a vast landscape of possible solutions, each corresponding to a different set of physical laws. Yet another arises from quantum mechanics, where the many worlds interpretation proposes that every possible outcome of a quantum event actually occurs in separate, branching universes. These different approaches do not necessarily describe the same kind of multiverse, but they share a common theme. They suggest that what we perceive as the universe may be just one part of a much larger reality. Each theory offers its own perspective on how multiple universes could exist and how they might differ from one another. Despite its appeal, the multiverse remains a highly debated idea. One of the main challenges is the lack of direct evidence. By definition, other universes would be outside our observable region, making them extremely difficult to detect. Some researchers have proposed indirect ways to test the multiverse, such as looking for subtle imprints in the cosmic microwave background that might indicate collisions between universes. However, such evidence is difficult to confirm and remains uncertain. This raises an important question about the nature of scientific inquiry. For a theory to be considered scientific, it must be testable and falsifiable. If other universes cannot be observed or measured, can the multiverse be considered a scientific theory, or does it belong more to the realm of philosophy? This question continues to be debated among scientists, with some arguing that the multiverse provides valuable explanatory power, while others caution against embracing ideas that cannot be empirically verified. Even without direct evidence, the multiverse concept has influenced how scientists think about fundamental physics. It encourages the exploration of a wider range of possibilities and challenges the assumption that our universe is the only one, or that its properties are uniquely determined. It also highlights the limitations of observation, reminding us that there may be aspects of reality that lie beyond our ability to measure. The idea of multiple universes also changes how we think about the origin of our own universe. Instead of being a singular event, the Big Bang could be one of many such events, each giving rise to a separate universe. In this context, our universe becomes part of a larger process, one that continuously generates new regions of space and time. This perspective shifts the focus from a single beginning to an ongoing cosmic creation. Another implication of the multiverse is the possibility of radically different forms of reality. In some universes, the laws of physics might be so different that familiar concepts like space and time may not apply in the same way. These universes could be fundamentally unlike anything we can imagine, existing beyond the limits of human understanding. While this idea is highly speculative, it underscores the vast range of possibilities that the multiverse allows. At the same time, the multiverse does not diminish the significance of our own universe. The observable universe remains a rich and complex system, worthy of study and exploration. The existence of other universes, if it is real, adds context rather than reducing importance. It suggests that our universe is part of a larger tapestry, one that extends beyond what we can see, but still connects to our understanding of physics and cosmology. The concept of the multiverse also resonates with deeper philosophical questions about existence and reality. If there are many universes, each with different properties, what does it mean to exist in one rather than another? Are there versions of ourselves in other universes living different lives under different conditions? While such ideas often enter the realm of speculation, they reflect the profound impact that the multiverse concept has on our perception of reality. In exploring these ideas, it is important to maintain a balance between imagination and evidence. The multiverse provides a framework for thinking about possibilities, but it also requires careful consideration of what can be tested and verified. Scientific progress depends on this balance, allowing new ideas to be explored while maintaining a commitment to empirical evidence. As research continues, new insights from cosmology, particle physics, and quantum theory may shed light on the validity of the multiverse. Observations of the early universe, studies of fundamental particles, and advances in theoretical models all contribute to this effort. While definitive answers may remain elusive, each step brings us closer to understanding whether our universe is unique or part of a much larger reality. The multiverse represents one of the most expansive ideas in modern science. It pushes the boundaries of what we consider possible, extending the concept of the universe beyond a single observable entity. It challenges us to think on scales that go far beyond even the vastness of the observable universe, inviting us to consider a reality that is almost limitless in scope. In the end, the multiverse is not just a scientific hypothesis, It is a reflection of humanity's desire to understand the deepest nature of existence. It shows how far we are willing to go in our quest for knowledge, exploring ideas that stretch the imagination and challenge the limits of observation. Whether or not the multiverse exists, the process of exploring it expands our understanding of the cosmos and our place within it. As we continue to look outward and inward, studying the universe at every scale, we are reminded that each answer often leads to new questions. The multiverse is one such question, vast and complex, offering both possibilities and mysteries. It stands as a testament to the boundless curiosity that drives science, urging us to keep exploring, keep questioning, and keep searching for a deeper understanding of the reality we inhabit. As we explore the vastness of the universe and push against the boundaries of observation, we eventually arrive at a realization that is both humbling and profound. There are limits to what we can know. These limits are not simply the result of technological shortcomings or gaps in knowledge that will eventually be filled. They are built into the very structure of the universe itself, arising from the nature of space, time, and the laws of physics. Understanding these limits is not a failure of science, but a deeper layer of it, revealing the boundaries within which all knowledge must exist. One of the most fundamental limits comes from the speed of light. Because nothing can travel faster than light, information is restricted in how it moves through the universe. This creates the observable universe, a region defined by how far light has traveled since the beginning of cosmic expansion. Beyond this boundary, there are regions that we cannot observe, not because we lack the tools, but because the information has not had enough time to reach us. This limitation is absolute, rooted in the fabric of reality, and it defines the edge of what can be directly known. This boundary is not static. As time passes, light from more distant regions continues to arrive, gradually expanding the observable universe. However, the accelerating expansion driven by dark energy introduces another limit, the cosmic event horizon. Beyond this horizon, events can never influence us, no matter how long we wait. This means that there are parts of the universe that are permanently beyond our reach, regions that exist but are forever disconnected from our ability to observe or interact with them. These cosmic limits shape not only what we can see, but also what we can test. Science relies on observation and experimentation, and without access to data, it becomes difficult to confirm or refute ideas. This is particularly relevant when considering theories about regions beyond the observable universe or concepts like the multiverse. While such ideas may be consistent with known physics, their lack of direct testability raises important questions about their status within science. Another limit arises from the nature of measurement itself. At the smallest scales, the principles of quantum mechanics introduce uncertainty. Certain properties, such as the position and momentum of a particle, cannot be known simultaneously with perfect precision. This is not due to imperfections in measurement, but a fundamental property of nature. It means that there is a limit to how precisely we can describe physical systems, a built-in fuzziness that persists no matter how advanced our instruments become. At the largest scales, general relativity governs the behavior of space and time. While it has been incredibly successful, in describing gravity and the structure of the universe, it breaks down under extreme conditions, such as those found at the center of black holes or at the very beginning of the universe. In these regimes, our current theories are incomplete, and a unified description that combines quantum mechanics and gravity remains one of the greatest challenges in physics. Until such a theory is developed, our understanding of these extreme environments will remain limited. The early universe presents another boundary of knowledge. While we can observe the cosmic microwave background and infer conditions shortly after the Big Bang, the very earliest moments remain inaccessible. The extreme energies and densities of that era push our theories beyond their tested limits, leaving a gap in our understanding. What happened in the first fraction of a second, or whether there was a state before the Big Bang, are questions that may require entirely new frameworks to answer. Even within the observable universe, there are practical limits to what we can measure. Distant objects appear faint and small, making detailed observations challenging. Intervening matter can obscure or distort light, complicating measurements. While advances in technology continue to improve our capabilities, there will always be limits imposed by distance, resolution, and the nature of light itself. The concept of limits extends beyond physics into the realm of human cognition. The universe operates on scales that are far removed from everyday experience. Distances measured in billions of light years, timescales spanning billions of years, and energies far beyond anything encountered on Earth all challenge our intuition. To understand these concepts, we rely on mathematics and models, tools that allow us to extend our thinking beyond direct experience. However, these tools also have limitations, shaped by the assumptions and frameworks we use to construct them. Philosophically, the limits of knowledge raise questions about the nature of reality and our place within it. If there are aspects of the universe that we can never observe or fully understand, what does that mean for our pursuit of knowledge? Some might see this as a barrier, a point beyond which science cannot go. Others see it as an invitation to explore new methods of inquiry, to refine our theories, and to expand our understanding as far as possible within these constraints. One important aspect of scientific progress is the recognition of uncertainty. Rather than seeking absolute certainty, science aims to build models that are consistent with observation and capable of making predictions. These models are always subject to revision as new data becomes available. In this sense, the limits of knowledge do not represent an endpoint, but a boundary that shifts as our understanding evolves. The history of science is filled with examples of boundaries that were once thought to be insurmountable, but were later expanded. The limits of the solar system gave way to the discovery of galaxies. The limits of visible light were extended by observing other wavelengths. Each advance has pushed the frontier of knowledge outward, revealing new layers of complexity and new questions to explore. However, the cosmic horizon and the fundamental laws of physics suggest that some limits may be more permanent than others. The idea that there are ultimate limits to knowledge can be unsettling, but it also adds depth to our understanding of the universe. It reminds us that the cosmos is not just vast, but structured in a way that defines what can and cannot be known. It highlights the interplay between observation, theory, and the fundamental nature of reality, showing how these elements combine to shape our understanding. In practical terms, scientists continue to work within these limits, developing increasingly sophisticated tools and methods to extract as much information as possible. Telescopes are designed to detect faint signals from distant galaxies. Particle accelerators probe the behavior of matter at the smallest scales. Computational models simulate complex systems, allowing us to explore scenarios that cannot be directly observed. These efforts push the boundaries of knowledge, even as they acknowledge the existence of limits. The limits of knowledge also influence how we interpret what we observe. Data must be analyzed within the context of theoretical frameworks, and different interpretations can sometimes lead to different conclusions. This requires careful consideration and a willingness to revise ideas in light of new evidence. It also underscores the importance of collaboration and open inquiry as scientists work together to refine their understanding. Another important aspect is the role of imagination. While observation provides the foundation for science, imagination allows us to explore possibilities beyond current knowledge. Theories about the multiverse, the nature of dark energy, or the origin of the universe all involve a degree of creative thinking. This imagination is guided by evidence and constrained by known physics, but it plays a crucial role in advancing our understanding. The balance between what is known and what is unknown is a defining feature of cosmology. Each discovery answers some questions while raising others, creating a dynamic process of exploration. The limits of knowledge do not halt this process, but shape it, guiding where and how we look for answers. As we consider the limits of knowledge, it is also important to recognize the achievements that have been made. Humanity has moved from a limited understanding of the night sky to a detailed picture of the universe's history and structure. We have measured the expansion of space, detected ancient radiation, and identified components like dark matter and dark energy. These accomplishments demonstrate the power of scientific inquiry, even within the constraints imposed by the universe. At the same time, the existence of limits ensures that there will always be mysteries to explore. There will always be questions that challenge our understanding, pushing us to develop new ideas and new approaches. This ongoing quest is at the heart of science, driven by curiosity and the desire to understand the world around us. In the context of the observable universe, the limits of knowledge are particularly significant. They define the boundary of what we can see and measure, shaping our understanding of the cosmos. Beyond this boundary lies a realm that is inaccessible to direct observation, yet it influences how we think about the universe as a whole. This interplay between knowledge and mystery creates a sense of perspective. It reminds us that our understanding is both powerful and limited, capable of revealing the structure of the cosmos while leaving some questions unanswered. It encourages humility, recognizing that the universe is larger and more complex than any single theory or model can fully capture. Ultimately, the limits of knowledge do not diminish the value of exploration. Instead, they enhance it, providing a framework within which discovery takes place. They remind us that science is not just about finding answers, but about understanding the questions themselves and the boundaries within which those answers can be found. As we stand at the edge of what can be known, we are faced with a choice. We can see the limits as barriers, or we can see them as horizons, points that define the next stage of exploration. In choosing the latter, we continue the journey of discovery, pushing the boundaries of knowledge as far as they can go, while embracing the mystery that lies beyond. In the vast structure of the cosmos, every answer we uncover seems to lead to a deeper question. The universe reveals itself not as a finished story, but as an unfolding mystery that stretches across unimaginable scales of space and time. From the smallest particles to the largest cosmic structures, everything we have explored points toward a reality that is dynamic, evolving, and still only partially understood. At the edge of what we can observe, we find not a final boundary, but a transition into the unknown, where knowledge meets uncertainty and curiosity becomes the guiding force. The journey through the universe begins with light, the messenger that carries information across billions of years. Every photon we detect from distant galaxies is a fragment of history, a record of events that occurred long before the existence of Earth or even the Milky Way. Yet even this ancient light has limits. Beyond a certain distance, it fades into the background of cosmic expansion, stretched and weakened until it can no longer be distinguished. This is not a failure of observation, but a reflection of the universe's structure itself, where distance and time shape what can be seen. As we reflect on the observable universe, we realize that it is both immense and finite. It contains billions of galaxies, each with billions of stars and countless planets that may or may not harbor life. Yet all of this represents only a fraction of the total cosmos. Beyond the observable boundary lies a realm that may extend indefinitely, filled with similar structures, or perhaps something entirely different. This unknown region is not hidden by walls or barriers, but by the simple fact that light has not yet had the opportunity to reach us, and in some cases, never will. This realization reshapes our understanding of existence. It suggests that the universe is not centered on any particular point, including our own. Instead, every observer, wherever they may be located, experiences their own observable universe centered on themselves. This symmetry implies that our perspective is not unique, but one of many possible viewpoints within a much larger structure. It challenges the idea of a privileged position in the cosmos and replaces it with a more universal principle of equivalence. Yet even as we acknowledge this vastness, we are also reminded of how far human understanding has come. There was a time when the universe was thought to be limited to the Milky Way, a single island of stars surrounded by darkness. Today, we know that the Milky Way is just one galaxy among countless others, embedded in a cosmic web that stretches across billions of light years. This transformation in understanding reflects the power of observation, reasoning, and imagination working together to expand the boundaries of knowledge. The expansion of the universe adds another layer to this story. Space itself is not static, but dynamic, stretching and evolving over time. This expansion carries galaxies away from each other, shaping the large-scale structure of the cosmos. It also means that the universe we observe today is different from the universe that will be seen in the distant future. As expansion continues, some regions will move beyond our observable horizon, gradually disappearing from view. In this way, the universe is constantly changing not only in structure, but in what can be known about it. Dark energy, the driving force behind this accelerated expansion, remains one of the greatest mysteries in modern science. It is invisible, undetectable through direct means, yet it governs the fate of the cosmos. Its presence suggests that the universe is influenced by components that we do not yet fully understand. Whether it is a property of space itself or a new form of energy remains uncertain, but its effects are undeniable. It shapes the future of galaxies, the evolution of cosmic structures, and ultimately the limits of what can be observed. The deeper we explore, the more we encounter questions that challenge the foundations of physics. What happened at the very beginning of the universe? Why do the fundamental constants have the values they do? Is our universe one of many, or is it unique? These questions do not diminish the value of what we know. Instead, they highlight the depth of what remains to be discovered. Each answer becomes a stepping stone toward a broader understanding, revealing new layers of complexity beneath what once seemed complete. At the smallest scales, quantum mechanics introduces a world governed by probability and uncertainty. Particles do not have fixed positions or velocities until they are measured, and their behavior is described in terms of likelihoods rather than certainties. At the largest scales, general relativity describes the curvature of space and time, shaping the motion of galaxies and the expansion of the universe. These two frameworks, while extremely successful in their respective domains, remain fundamentally incompatible in extreme conditions. The search for a unified theory that can reconcile them continues to be one of the central goals of physics. This ongoing pursuit reflects a deeper truth about scientific understanding. Knowledge is not a fixed collection of facts, but a continuously evolving structure. As new observations are made and new theories developed, our picture of the universe becomes more refined, but also more complex. What once seemed simple often reveals hidden layers of structure, and what once seemed certain becomes subject to revision. This process is not a weakness of science, but one of its greatest strengths, allowing it to adapt and grow in response to new evidence. In contemplating the universe, we are also confronted with our own place within it. We are observers embedded within the very system we study, limited by the same physical laws that govern everything else. Yet within these limits, we have developed the ability to ask profound questions, build instruments that extend our senses, and construct theories that reach across billions of years of cosmic history. This ability reflects not just technological progress, but a deeper capacity for understanding and curiosity. The future of the universe itself remains uncertain in many respects. While current observations suggest continued expansion and gradual cooling, the full long-term fate of the cosmos depends on factors that are still not fully understood. Whether the universe will continue expanding forever, approach a steady state, or undergo more dramatic transformations depends on the nature of dark energy, the behavior of gravity on large scales, and other fundamental properties that are still being investigated. What is clear, however, is that the universe is not static. It is a process, a continuous unfolding of structure and change. Galaxies form, evolve, and interact. Stars are born and die. Space itself expands, shaping the large-scale distribution of matter and energy. Even the laws that govern these processes are subjects of study, refinement, and deeper inquiry. The universe is not a finished object, but an ongoing story. At the edge of this story lies the boundary of observation, the cosmic horizon that defines what we can see and what remains hidden. Yet even this boundary is not absolute. It shifts over time, influenced by expansion and the flow of light across space. It reminds us that knowledge is always partial, always situated within a broader context that may extend far beyond our reach. And yet, within this partial view, there is immense richness. The observable universe contains enough complexity to occupy generations of study. From the formation of the first atoms to the emergence of galaxies, from the behavior of black holes to the structure of cosmic filaments, every scale reveals new patterns and new questions. The universe does not need to be fully known in order to be deeply meaningful. Perhaps the most profound realization is that mystery is not a barrier to understanding, but an essential part of it. Without unknowns, there would be no exploration. Without limits, there would be no horizon to approach. The unknown is not separate from knowledge, but intertwined with it, shaping the direction of inquiry and giving it purpose. As we conclude this journey through the edge of the universe, we are left with a sense of perspective. We see a cosmos that is vast beyond comprehension, yet structured in ways that allow us to understand parts of it. We see a universe that is expanding, evolving, and possibly infinite, yet still accessible to human thought and investigation within certain limits. We see ourselves as small within this vastness, yet capable of grasping ideas that span billions of light years. The edge of the universe is not a place we can reach, but a concept that defines the boundary of our vision. Beyond it lies not emptiness, but possibility. Possibility of more galaxies, more structures, more laws of nature waiting to be discovered or understood in new ways. Whether or not we will ever observe what lies beyond, the act of questioning it already expands our understanding. In the end, the universe invites us not to final answers, but to continuous exploration. It is a reminder that every discovery opens new doors, and every boundary reveals a larger landscape beyond. The edge of the universe is therefore not an end, but a beginning, a starting point for deeper inquiry, broader imagination, and an ever-expanding search for meaning within the infinite.